So we're one step closer to actually solving differential equations using Laplace transformations. So the process we're about to do and how this is going to work using it is we're going to start with a function f of t. We're going to transform it using the Laplace transform f of s. Okay. Do our stuff in here, and then afterwards reverse it back to what we want. Okay. So the question is, how do I reverse it? And well, we got to find the inverse of this Laplace transformation. And that's what we're going to be doing here. So how do we go backwards? If I give you the Laplace transformation, what was the original function we dealt with to begin with? Okay, so this is actually quite difficult to do by. So we're going to, I guess it's not cheating, but it's just no way we know, right? So there's no point in inventing the wheel when we already have the wheel to begin with. Okay. So a lot of this is just going backwards and identifying which scenario we're actually in. Okay. But before we get there, we'll just a quick definition of what it really means by the inverse. So given a function capital Fs, so the Laplace transformation, there is a function f of t that's continuous from 0 to infinity, such that this is true, right? That's what this represents. Therefore, f of t will be the inverse of the Laplace transformation, defined by this. Now, just like the one when we came to additions, same thing applies for Laplace inverses. So if I want to find the inverse of two functions being added together, I can split them up, find the Laplace transfers individually, and then put them together. Same thing with a constant. I could bring it to the front, do that first part, and then multiply by the constant again. Okay. Now, like I said earlier, we're not going to cheat, but we're not reinventing the wheel. So what we're really going to do is figure out which situation, and when it comes to the tables, we're going to have far more in detail. So it's actually going to look like this. The tables are drastically huge for each Laplace. So these are the most common ones used. Obviously, there's far more and far more elaborate, as you could tell. We're not going to use them all, but there's some we're going to basically use over and over again, like the basic ones themselves. Okay. So how are we going to do this? Use this table going forward. So here we want to find the inverse Laplace of each individual case. Or what was the original f of t function? That's what we're looking for each case. Okay, so let's look at the first one. So this is 2 over s to the third power. Okay, so if I follow this process, so constant or something over s to some power. And again, it's pretty much like finding Waldo, or we just want to match respectively what goes where. Okay. So again, because we're going backwards, we're actually not looking at f of t, we're looking at its respective Laplace, right? So we're actually going here and going in this direction. Okay. So kind of follows a process, right? We just got to match each one individually. So it looks like our case here might look like, let's say maybe 16 it looks like, maybe. That's kind of about what we have here going on. I guess it could be this one as well. A will be 0. So, but if A is 0, we actually get this back anyway. So it looks like our situation is going to be here. So, which makes sense, right? If n is 2 and n plus 1 is 3, so that checks out. So here n is going to be 2 in our situation here. All right, so this process looks like n factorial over s n plus 1. So when n is 2, so if I just go backwards, therefore this is going to be, so our original function, f of t, will be t to the n power, or just t squared. And that's how we use the tables to go find the inverse Laplace of this transformation. So again, this is technically our last step to solving for differential equations, going backwards now. Okay. All right, so let's try the next one here. And we're going to change this up here. It's actually not possible if I kept it the same. We change it to a squared instead of a cubed. Okay. All right, so what does this one look like? So we have constant over s squared plus something. So let's see. Nothing down here. Maybe on the other side now. Okay, this looks promising here. So this is S and S, so we don't have S and S. We have constant and constant, so maybe this is that's one good candidate. We have plus 9, so not minus, so that's not going to be it. Okay, so it looks like we got it right here. But again, I want this in the same process. These b's are the same. This is just being squared, which does make sense because if b is 3, then we have 3 over s squared plus 3 squared, which is exactly matches what we have here. Perfect. It works. So this Laplace is sine of bt. So f of t will be sine of 3t. Okay. All right, let's keep going. So now it gets a little bit more difficult and not as obvious, let's just say, right? So now we have something at the bottom. So the key thing is we want to factor. So the factorings are down here. But unfortunately, I don't think this factors nicely. It's actually not possible to factor. So that's not going to work. Okay. So the next things I guess we can do, there's nothing that has a polynomial on the bottom, it looks like. So I guess we have to do something that's everybody's favorite. Complete the square. So by completing the square, that means b is going to be negative 2. So I'm going to add and subtract negative b over 2 squared of both sides, or just negative 1. So 1 itself. So in the bottom, I'll just look at the bottom, it's going to be s squared minus 2s plus 1, and then minus 1 plus 5, like that. Again, just look at the bottom, right? So this now becomes a perfect square, which does. This ends up being s minus 1 squared when you factor, and this ends up being plus 4. Okay. So on the bottom, we now have s minus, well, on the top we have s minus 1 over s minus 1 squared plus 4. Okay, so now, since we completed the square, hopefully this looks like one of them of the completed square part, which is these situations right here. So let's see. So it looks like top and bottom are the same here, which is what we have. Top and bottom are the same. And here we go. So we have a and b. So it looks like a is going to be 1, and b is squared. So something squared gives you 4. It's going to be 2. So we have a equaling 1 and b equaling 2 here. And this Laplace transform goes across is e. So we're going to have e raised to the at, so 1 times t, cosine of 2t. And there's our Laplace transformation. Right, so now let's go to the subtraction one. So this is where this comes into play. So all we're going to do is find the inverse Laplace of each individual case and then add them together at the very end. Okay? And we'll actually be using both of these theorems here. Okay. All right. So first one, I'm going to get rid of that 5 and put that in the front. Okay. I'm also going to bring the 6 to the front as well. Ooh. So we actually had this earlier, right? So it might be the other one. So I'm just going to have 3 squared, it looks like, because that's what we had earlier. Might not be sine, but might be cosine instead. And this one, See, if I factor out a 3 and also factor out a 2, this leaves me with xs squared plus 4s plus 5 on the bottom. Okay. Okay. And, oh, it's not the same thing. Okay. All right. So let's look at the first one. So 1 over s minus 6. So 6 must be a constant. So let's see what we got here. Might be this one here. 1 over s minus a. So in this case, a is going to be 6. So this Laplace here is going to be e raised to the at. So, oh, times 5, so 5 e to the raised to the 6t. Okay, minus 6 times this Laplace. And we had sine earlier, so I'll just go up to the sine already. And it looks like now just cosine instead, because we have s squared. So that's exactly what I have, s squared and s, so it was a good thing. So b is going to be 3 this time. Where was it? Here it is. So there we go. So this is going to be 6 times cosine of 3t. Okay. And now the last one, hopefully we can factor. If not, we'll just do the same thing we did last time. And let's see, it's 5 and 4. Now I don't think it looks like it. So again, we have to do complete the square method. Right? So completing the square at the very bottom, I'll just give you the answer. It's s plus 2 squared plus 1. Same thing, right? b is 4, so we do 4 over 2 squared, so just add and subtract 4. So add 4, subtract 4, that's how we get the 1. Okay? Alright, so this Laplace is going to be the same as, oh, very similar to this one, so it might be just the sine of it. So where is that sine of it? Let's see if that's true. Okay, and it looks like it is. So in this case, a is going to be negative 2, and b is going to be 1. Okay. So now, over here, I'll just rewrite it. Okay. So plus 3 halves times this Laplace is going to be e raised to the negative 2t sine of 1t. And there we go. So that is our Laplace there. So lots and lots of information there, right? So slowly break it down. Again, the whole process is just literally just finding which one goes to it. Okay. So now let's find one that's not so fun to do. So, and I kind of get the hint, it has to do with partial fractions. This is a fun one, which is really not good at all. Okay, so how are we going to do this partial fraction stuff? So first off, when I give you the hint of partial fractions, I got to split up the fractions somehow. Unfortunately, I cannot actually break up the bottom so to a nice beautiful one, so we'll just keep doing the same process we've been doing, completing the square. Okay. So in this case, completing the square will be 2 over 2 squared is going to be 1, so I'm going to add, subtract 1 to this bottom part. So when I do that, I end up getting s, plus 1. S plus 1, and then minus 1 gives you the 9. Okay. So already off the bat, you can kind of tell, hopefully, from the past examples, that. Okay. All right. So what I mean by partial fractions is this looks very similar, right? If I just block this off here, and just look at the bottom, this is starting to look like one of these. That one and that one. Okay, so because notice they have the same bottoms, but the tops is the only difference. So it looks like it could be one of these two is going to be our answers, right? But since it's a combination, we're going to see, well, what if, oh, for example, here we have on the very top, it's 3s plus 2. So if we split it up, it's probably be a combination of both, because this one only has a constant, and this one just has a constant minus a value, not a constant in front of the s. Okay, something we don't have here. So it looks like these is a combination of these two put together. That's where the partial fraction comes into play. Okay, so if you just remember partial fractions, it's not as elaborate as finding repeated roots and that craziness. Well, it can get that difficult, but it's not that difficult in this case. But the top is going to now look like this. Well, I'll just go through the whole process. So partial fractions is going to be a times, and I'll just use, so because let's say this one, first part has to be s minus a, I'll just put that s minus a all over the same process, plus b times the other part, which is just a b term. Now, maybe wondering, that's a lot of letters, lowercase and uppercase, but we actually know what little a and little b are on the situation. So again, we're just going to go situation-wise. So s minus a on top represents the cosine function, and the a over here is the same as the a over here. So in this situation, this is going to be equal to 1. Okay. Now on this side, this is equal to the sine part, where b is the same as this b down here. So it's going to be 3. So now it's our job to figure out what the capital A and the capital B are in this partial fraction decomposition. Okay. Now, the best part is, because the bottoms are all the same, you don't have to cross multiply and figure what they're missing. You could just equal the top. So in other words, since everything's on the bottom the same, because there was no really factors to split up, we end up just having this. Oh, this is a 1. So then we just distribute And again, the best part of partial fractions, right, and the solving for it is now we have a system of equations. So we know that this part, all of this must equal all this part, right, and including its individual parts. So since none of this has a variable, that means this whole thing has to equal 2. Well, this is the only thing that has a variable, has to equal the only thing that has a variable over here. So right off the bat, we know 3 must equal a. And therefore the other situation, so 2 must equal negative a plus 3b. And since we already know what a is, we just plug it in. And now we can just solve for b. So something's wrong here. This should be plus. Yes, because a is negative 1. Okay, sorry. So my mistake. So this is going to be a plus here. This is a plus here, plus here. Okay. So subtracting this over gives you negative 1. So therefore b is negative 1/3. Okay. So now, reverting ourselves, this process, well, the a is 3. So it will be 3 times s plus 1. That's where I made a mistake here. It's actually plus 1 minus 1/3 times the rest of it. Like that. Okay, so now, just in case you forgot, the first part, the s plus 1, represents the cosine of it, where we have a and b here. So this is where a is -1. I did it again. A is -1, and b is 3. So it'll be 3 times e to the negative t power cosine of 3t minus 1/3, and this is the sine of it. So again, a is the same, which is nice, so it's -1, b is 3. So if you notice, this is now showing like a solution to either a particular situation solution or a homogeneous solution, because we have the imaginary numbers part, which kind of makes sense, right? Because if you solve for it, you actually get imaginary numbers for these the factors. So, little precursor of what this is actually useful for, right? So this is like y1, this is y2. This is c1, c2. Okay. Now, last part of this portion is just a refresher of partial fractions, the different situations. So, for example, if you have distinct roots, that's just saying you have a over the individual root itself. The other one is if you have repeated roots, that means you have one for each individual term you have here. And the last one's the most difficult, is when you don't have any factors all broken down, meaning unfactorable, kind of like the same situation we have up here. But since we didn't have any s squared, which is nice, we just didn't break it down. So this only works when the upper is larger than the bottom. So this kind of situation, you get ax plus b over this. And then you can solve for a, b, respectively, just going from the top. So it's kind of like what we had above, right? And it's exactly what we had above. But the best part is we're doing Laplace, so you're actually already known this format here, which is kind of nice.